Today I'm going to be presenting my material science project on the mechanical properties of composite solids. So to start off, composite solids, pretty self-explanatory, couple more, two or more, materials being mixed together and to have different properties. The whole point is to get different properties out of it. So their properties do change when they mix together, and this could be due to a numerous amount of factors of like interactions between the two, density changes, blah blah blah. So basically, the properties when they get mixed together, they aren't guaranteed to be smaller in the middle or higher than the original, but for most composites, I would say, based on my research, their hardness and strength to weight ratio are known to be stronger than their individual pure components. So, the mechanical property tests that we've learned previously in Chapter 6 are tensile, torsion, fatigue, fracture, compressive, creep, hardness, and a bunch of others, but those are the main ones I included in my presentation. I'm going to be doing ones with tensile, which is pulling the sample and seeing how the atoms arrange. Torsion, twisting the sample, seeing the exact same thing how atoms rearrange. Compressive, opposite of tensile, instead of pulling, I'm pushing the material on top of itself. And hardness, which is similar to compression, except I'm taking, or one, it takes a sample and presses it into another based on a certain amount of load force and seeing how that sample reacts to the deformity. So my hypothesis before I started the experiment was I thought that the composites are generally going to have better stress and better strain properties than the material, and especially composites with more components. So the tests I'm going to be performing today are compression, tensile, and torsion, and then I will also include the cross-sectional areas of each sample to show the density, just an observational density and how much impurity is present, just to get a visual when making some of these conclusions. So the experimental setup, I'm using Play-Doh as a base because it's malleable and it allows me to easily manipulate and perform these hands-on mechanical tests, and I'm going to be adding different amounts of rice and glitter to them. I will do some cross sections and then perform the mechanical tests and then record any lengths of breakage, deformity, and I will show you the results. So the samples I used are 2-ounce containers. Most of them are going to be starting in a circular ball when I perform these tests, just so that each sample is being subjected to the same amounts of compression or tensile strength, where they all are at the same starting point. It's a better example. They're at the same starting point, so there's little to no discrepancy and bias when performing these. And each of these has a little rice. Or I'll show you. A little rice is present in this sample. A lot of rice, a lot of glitter, a little amount of glitter, little amount of rice and glitter, and then we're doing a control, which is nothing in the sample at all. So for the results, I'll show you guys, this is the cross sections. Well, you can kind of see there's a lot of air bubbles present when adding impurities into these solids. That's something that I took into consideration when looking at this. But as you can see, I tried to really load them with a lot of impurities, especially the glitter. So these two pink colors are glitter samples. This green is pure. This one has rice and glitter, and the blue ones over here just have rice. So after this tensile strength pulling, I realized that the clear one has about 15 centimeters worth of breakage, and our lowest, which was rice, had about 10 centimeters before it broke. And it's kind of interesting to also look at how they break as well, like based on the shape of them. So here's twisting, still Play-Doh, twist very well, clear Play-Doh, just twist very well. And we had that the pink and the blue the ones packed with more impurities had less resistance to turns. And when I twisted the sample, and when as soon as it broke off, that's when I did my cutoff point. So here's another compression test that I did. I took two books and basically laid it on the sample, as you can see in this little picture right here. I recorded the diameter before and after they were compressed and measured the distance and got the thickness change between all of them, which was between a half to 1.5 centimeters. Some conclusions that I reached when I was doing our test was elasticity tends to increase with purity. As we saw, the pure Play-Doh was the one that had the longest stretch, and the one with a lot of rice, which it's think like normal long grain rice, has a higher surface area and volume. That one led to the shortest stretch. And the cross sections I kind of touched on already. The relative density of the impurity tends to be high, showed you how much it can have an effect on. Just to add a visual example to the resistances that I'm about to talk about. So torsion also increases with purity. Again, pure dough had more twists available. High rice content and high glitter content had the least amount of twists. Resistance to loads decreases with purity. Now this makes sense because with the compression testing, we saw that there was a lot more compression from the pure samples as Play-Doh. It had the biggest radius change, and then with high rice content, it changed like half a centimeter from two hardcover heavyweight books. So basically, the takeaways I can get from this are that adding the impurity is just it does show evidence to support that properties do tend to increase. However, the strain decreases with impurity. And when I also noticed it, I saw a lot of brittleness and breakage with more impure substances compared to the initial Play-Doh. And that can lead to brittleness and crack. And I guess there is a certain role that the size of particles play when altering these properties, and basically that there is such thing as a breaking point when you are making these samples. So there's like a tolerance, if you could say, for these composites when creating them. That's something that creators have to take into consideration. So, and those are my sources. Thank you for listening. Have a good day.